reaction in both, with both an acyl chloride and an anhydride. But you're aware that when we get to the ester and the amide, we actually need to add something to make the reaction go. So while no reaction might not be exactly the right language, I think really what we're trying to say is it's not a productive reaction, right? That water alone is not going to efficiently get you complete conversion to a carboxylic acid. I'm sure you get a tiny bit in the flask. So pretty much when we get down to the ester or the amide, we either need to add an innocuous acid like H2SO4, H3PO4, or a base, NaOH, KOH, something basic to get back to the carboxylic acid. Okay? So I'm going to run a couple of these reactions with you. Okay? I'm going to sort of talk about the tricks of the trade, and then I'm going to unleash you to try the workshop. There's a handout today that is two-sided, okay, and we'll hand this out after we go through the initial lecture today. The first side has both workshops we're going to do this week, A and B. A is what we'll be working on today. Those are the hydrolysis reactions. So what they do is they give you names of compounds and reaction conditions to show the products. So it's a way to test your nomenclature as well, and this is likely how they'll be written on the exam. So it gives you practice sort of to get exam level problems under your belt. On the back are the structures written out so that you can check that your names are correct and that the structures you're getting are correct. So all the just base answers are on the back. The mechanisms will be in a separate handout that will be placed online because it's like 10 or 12 pages this weekend. Okay? So, to start going with hydrolysis, we want to look at maybe one of the mechanisms that require water only, and then I'm going to start talking about these esters and amides and the difference between the acid-catalyzed and base-promoted reactions. Okay? So if I choose one to do just the water addition, we know that the electrophilic center is good enough here to allow attack of water, sufficient attack of water, to create a tetrahedral intermediate. Now, it doesn't matter which carbonyl you attack first. You're never going to be tested on that. It's a good question. It's one I get eventually, but you're not going to be ever asked to indicate which carbonyl would be more likely to be attacked. So you choose one or the other, and what you're aiming for here as the nucleophile attacks one of these carbonyl centers is to form a tetrahedral intermediate. That's what we're always looking to do when a nucleophile, right, attacks a carbonyl carbon. So in this case now, we see the formation of that tetrahedral intermediate. Since we're in neutral water, we are allowed to have both positive and negative species in solution, right? It only matters that I have only positive or neutral in acidic conditions, and only negative and neutral in basic conditions, but I have added no base or no acid, so I'm not limited. So my intermediate currently has two different charge states. Okay? You generally are not going to see an intramolecular attack here, so don't show the intramolecular attacks. That's a really good cheat, especially when you look online for some of these generic mechanisms. They sort of like to do that. In this case, this will be water that's deprotonating to create now the tetrahedral intermediate that we want to look at collapse for. Okay? So this has to be formed in order to efficiently get a new and novel product, because this guy is going on, off, on, off, on, off, on, off, right? So this first step is reversible. The second step is reversible because I can protonate, deprotonate, protonate, deprotonate. Okay? In this case, though, when I see collapse of the tetrahedral intermediate from this species here, I only have one good leaving group. Okay? I have two bad leaving groups and one good leaving group. This guy is a good leaving group, right? It's generally, its pK of a conjugate acid is 5-ish, right? OH minus would be 16. It's never really a good leaving group, right? We generally don't see it. We are going to see it in some cases, but it's not in neutral conditions a good leaving group because we're generating something that's unstable and very reactive, okay? Certainly we're not going to lose R minus, right? So if I analyze this, I'm going to lose the most likely thing, which in this case is the acetate, right? So here is the, well, it's carboxylate. This isn't necessarily acetate, right? So it's a carboxylate that comes off. That's what's come off here is the leaving group. when the tetrahedral intermediate collapsed, and I have created a mole of the carboxylic acid. Okay? Carboxylic acid is neutral. That's what the tetrahedral intermediate collapsed to. And the carboxylate is negatively charged. The leaving group in this case is negatively charged. Okay? So, in neutral conditions, when we come around in this last reaction arrow, okay, to show the collapse of the tetrahedral intermediate, we need to question whether or not the tetrahedral intermediate can be reformed readily, right? And the answer is no. Okay? The answer is no. You formed a carboxylic acid, and a carboxylic acid doesn't have as reactive a carbonyl center, right? That's number one. And number two, you're promoting the addition, or you're trying to promote the addition of a weak nucleophile, right? Which isn't necessarily going to gun for that carbonyl center. So in essence, when you let off a good leaving group, of which acetate is okay, right? These reactions are generally irreversible. Every reaction has some reversibility, but certainly if you can generate a good leaving group, right? An obvious leaving group, that's, an obvious one, these reactions become irreversible. And this is what you always want to be considering, always generating, right, a leaving group that is a good and adequate leaving group. Okay? So, we come back and review again. This is a, yeah.
Can you just reiterate what you said at the beginning? The first reason, what was it?
The first reason was that the carbonyl center is less reactive, right? When we are looking at the carboxylic acid family, the carboxylic acid is on par with the ester, right? So its carbonyl center isn't as reactive. So you really need something good to get in there and run for that center. Acetate, we know, is not a great nucleophile. It's okay. It's an okay leaving group. It's an okay nucleophile. It doesn't have enough chutzpah to get in there on its own. Okay? So these are conditions. Do you like my chutzpah? Yeah. I know. I can do the. We were just talking about this again. She's not even paying attention. Okay, that's good. Yes, we were talking about you, Kim. It's good. Okay. So, this is an example of neutral conditions. So this is the type of mechanism you're going to see with acyl chlorides and anhydrides. Okay? Water alone is enough to promote the hydrolysis reaction. Okay? The last step being irreversible is in essence saying, I have an adequate yield of product, water alone is enough. Okay? Are there questions about this in general? Yeah?
So does the leaving group pick up a proton off water?
Okay, so the leaving group could pick off a proton off of water. Absolutely, that would be a favorable, right? You would think that's a favorable reaction. You can look at that. So that everything has an answer in acid-base land. So this is my acid-base reaction I'm looking at, right? So this would be this and OH minus. This is 5 and this is 16. So the answer is no, right? See how I came up with that answer real fast? You're just like, whoa, holy moly, right? Whoa! So the question is the carboxylate going to be protonated in these conditions, the leaving group? The answer is you only have water, right? You have water and you have a carboxylic acid. Now, it should be apparent that if you pull from the carboxylic acid, you're just 50, 50, 50, 50, right? I mean, it's just sort of moving back and forth between the same species. It's not very productive. But it cannot pull from water, right? Because it's not strong enough to pull from water. So what I do is I let water be the acid and my carboxylate be the base, and I write my conjugate acid and conjugate base, and I look at my acid on each side and I assign a pKa, which are what the numbers are below those. 16 is below water, that's its pKa, that's the acid on the left side. 5 is below this carboxylic acid, the conjugate acid, on the right side. And I know reactions go strong to weak, so this reaction is not promoted in the forward direction as written, right? It's in essence saying I'm going to have a lot more of these species, right, at equilibrium than I am of the protonated carboxylic acid. So this is a place where you'll get 1 mole off sufficiently, but if you want the second mole, you need to protonate it, right, and collect the second mole. This second mole of carboxylic acid is ionic and will absolutely, right, can't be generated without giving some acid to the solution. Yeah?
Don't you have H3O+?
No. No. There's no H. Oh, is there a little bit of H3O plus? Yes. And then it's killed by this. This is a good question, actually. This is a good question. But that proton is moving all around, right? Generally, if it runs into H3O plus, it can do it. But there's not enough of that in solution. Yeah. Okay. Yeah.
Should we just draw one arrow for that one then, just so it's not confusing?
Sure,
or?
you can draw one arrow. I mean, I'm always here saying things are reversible to some extent. There's a reason that we talk about it that way. It comes up pretty shortly, actually. Okay. All right, so you get the general mantra of neutral conditions. All right. So here's the mantra when we get to these conditions over here. I'm going to have two choices. Okay? And I'm going to frame this out for you. I'm in essence giving you the answers, and I'm going to do one of them with you. But I want you to do all of the ones in the interconversions today so you see it in every single case. Okay? So here are the answers. I can, for esters or amides, like I said, I'm able to run these reactions in acid or base. Okay? If I run them in acid or base. We already alluded to, but I'm here to remind you, that if you run these reactions in acid, that's one potential, right? Make the reaction happen, because water alone is not enough to promote the hydrolysis reaction. If I run these reactions in an aqueous acid, so H2O and H2SO4, this is the absolute reverse of Fischer esterification, right? We said it's the reverse of Fischer esterification. So this mechanism is fully reversible. Just like you can take a carboxylic acid and an alcohol in acid to give me the ester, I can take the ester and water to give me back the carboxylic acid and alcohol. Fully reversible, okay? So that's not necessarily the best way for conversion. If I'm looking for complete conversion, good product yield, fully reversible reactions are not necessarily the way to go, right? They require a lot of work. You got to be in there, with these reactions, making sure you're pushing them toward the product that you want, right? In this case, you would add a lot of water. You'd want to collect the alcohol product so it comes off the reaction mixture and helps pull that reaction toward hydrolysis. So not the best. When I get to base, though, so when I start working in OH minus in H2O, so that's dumping in like 2 molar sodium hydroxide or something. That's a sign, right, that I have some water and some OH minus. Right? By 15 molar hydroxide, I don't have a lot of water there, right? Pretty much I'm only in a strong base. So we're talking about an aqueous base solution here. This reaction is irreversible. And the irreversibility of this reaction actually comes from the last step. The last step is an acid-base step, okay? The last step is an acid-base step. It's the very last step that we're going to look at. So I'm not writing that there, but you can write it next to the acid base. You want to write last step. You'll see it as the last step. That makes the entire reaction irreversible. Okay? The entire reaction is irreversible. When I come to the amides, what I find, same conditions, right? I can either do it in acid or I can do it in base, but each of these reactions are irreversible. They're each irreversible due to the very last acid-base step. So what you want to do is you want to get out there, right, and really understand the acid-base chemistry that's promoting the irreversibility of these mechanisms. Okay? This is the answer. All right? So this means, if you think about it, I'm here to remind you that at the end of H3O plus, right, when you're in acid conditions, your products better be positive or neutral, right? Your acid-base chemistry is never going to generate a negative charge anywhere. It's going to be positive or neutral. When you're in base conditions, your very last acid-base chemistry step is going to promote, right, formation and creation of negative and neutral, okay? Be careful, because you have the tendency to, stick those protons back on because you think they should be there, okay? What should and is there are two different things. So let's look at one of these. I'll take the ester, and I'll run through the reaction. This is generally what you're going to see, okay? Okay, so the ester would be something like OR. We're going to add OH minus here. as our reactive nucleophile. We know there's water in the pot. I'm just putting OH minus because that's what I'm going to use initially. There's water in there. Okay. So we see direct attack at the carbonyl center. OH minus is good enough to directly attack that carbonyl center. So onward it goes. It forms directly a tetrahedral intermediate. Okay? Now, this should be pretty apparent that that OH minus can come off, right, just like it came on. Now, that's, I shouldn't say readily apparent. This is not readily apparent. That's what I meant to say. It's not readily apparent to you how OH minus is just going to come off that thing, right? Because you've always been taught that OH minus is a bad leaving group, a bad leaving group, a bad leaving group, right? We were actually just talking about how OH minus was a bad leaving group. But here's the difference. When I'm in basic media, when I'm in a basic environment, that OH minus is coming off and blending into this great intermolecular attraction network, this network of intermolecular attractions. It in essence becomes solvated, and solvation always brings down the energy, okay? So in basic conditions, you can actually see bases as leaving groups. So this can come on, and it can come off for solvation. Just like what we'll see in the forward direction, OR minus coming off. OR minus can come off as well. If you think about OR minus compared to OH minus, they're really not that different. They're each solvated, right? It's not, they're really no difference there. So what I get out of this then is a carboxylic acid. This came from the collapse of my tetrahedral intermediate and my leaving group. Here's my leaving group. Okay? What you see as the very last step here is a very exothermic acid-base step, which sits to the right. Okay? If I write out the product to this acid-base step, I get the carboxylate, so RCOO minus, the carboxylate, that proton was pulled from the acid, and I get the conjugate acid of my leaving group, which is HOR. Okay? This is what I get. I know what the base is. It's always the guy with the negative charge, right? Negative and neutral, it's the negative guy. This is obviously the acid, named a carboxylic acid. The proton moves from the acid to the base, forming thus the conjugate acid, and leaving behind the conjugate base. I write down the pKa's of each of these things. This is 5, this is 16, this reaction sits to the right. Okay? And because of this, now exothermic acid-base step draws the entire product this way, right? Anytime I draw off product, I'm in essence pulling the reaction toward that last exothermic step. It's like a tug of war, because this is getting removed from solution, so the reaction keeps coming this way. Okay? So what you want to look at the end of each one of these irreversible steps is to look at, right, what's generated from the tetrahedral intermediate collapse and the leaving group. Right? The leaving group is your base. The collapsed tetrahedral intermediate is your acid, and you're looking at that last acid-base step and proving to yourself that it's exothermic in nature, favored, moving to the right. Okay? Are there questions about this one? Yeah?
The second arrow is equilibrium, right? Or is it only one line?
So what is this reaction here? So this reaction actually is not. Now that's because, right, the collapse doesn't allow necessarily for that reformation, right? So in essence, drawing this way. Once you have now the ability, right, for this to come off, the acid-base chemistry happens before any back attack, right? It's a good question. She's focusing right here. She wants to know, why isn't this step reversible? Okay? Here's the answer. These are the products of this step. Okay? This guy is going to behave as a base far faster than it's going to behave as a nucleophile. Hence, no back attack. No back attack. Daniel, was your hand up?
Yeah. How do we know it's an exothermic reaction?
So exothermicity is generally, yeah, I should be very careful about it. It's not like wildly exothermic, like OH minus and H plus, right? 55 kilojoules released per mole. No, but it's exothermic because the product is favored. And the product is favored because it's a weaker acid on the product side. So I'm not suggesting, blowing up. I'm just suggesting favorability. Okay. Yeah.
I was going to say another reason why it doesn't go bad because it's a good leaving group, like you're saying, you get a good leaving group to come off.
That's that's another potential argument. Okay. Yeah.
Why doesn't the OH behave as a base before it behaves as a nucleophile instead of pretty consistent?
Okay, so there is nothing here for the OH minus to really be pulling necessarily efficiently. Okay, that's a good question. The most acidic proton in this molecule here, I have an R group. I'm about to make it something, so let's make it CH3. The most acidic proton is this guy here. Okay, and OH minus doesn't pull this off favorably because the ppA here is like 20 to 25. So I don't necessarily have a favorable acid-base reaction. Okay, and that's it. This is the most acidic guy I have in there. So great question. Yeah. Okay, yeah.
You said that the irreversibility was determined by like the last step
Yes.
in the acid-base step, but here the last two steps are irreversible?
Right. But the fact is that this, right, irreversibility, that's speaking to this irreversibility, right? If this didn't behave as a base almost instantly, there would be some reversibility here, right? So yeah, in essence, this has caused an effect here, right? So it's really based on the last step. But your point is well taken. Yes, the last two steps have non-reversible arrows. So point well made. Okay. The last thing I want to remind you is, because I didn't do the acid version, but please remember that in base you see direct attack of OH minus, right? In base you see direct attack of OH minus. In acid, please remember that we've got to follow all of our rules. If I add H2O and H+, the first step is protonation of the carbonyl, right? This is all protonation of the carbonyl, attack, deprotonate, protonate something new. These are the mechanisms you all don't like, but they're here to stay, okay? So please remember all the tricks that we've learned with ketones and aldehydes and try and apply them into this material. This might help as you're looking over your old material as well, okay? All right, we're going to hand out the workshop. You can start working in groups. You can spread yourself out if you want. Kim and I are here to answer questions. I see Kaylin's here too, so we certainly can answer questions if you have them. Daniel's probably somewhere in the room. Yep, there he is. So we're happy to help you. If you have questions, by all means, ask them, because no question is a dumb question.